All right, so we're in section 3.5. Parallel postulate. And triangle sum. So before we write our postulate, let's remember what a postulate is. What did we say when we're talking about postulates, what are we talking about? Postulate is something that we accept as true without proof. So postulates are kind of in math and in geometry, there are building blocks. We have to start somewhere with things to build on. And in geometry, the postulates are some of those things that we start building on. So our parallel postulate. Our parallel postulate says that we're going to be given a line L. And a point P not on L. So here's what we have. Let me draw a picture down here. Here's line L, and we have a point P up here. And all of this is, we're talking about in the plane. There's our picture. The parallel postulate says there is exactly one line through P parallel to L. So if I want to draw a parallel line, I'll draw it in blue here. There's my line. And what the parallel postulate is telling us is that this line is the only one that goes through P that's parallel to L. That's the only one. There's no other way that I'm going to get another line to go through that point parallel to line L. That's our parallel postulate. Now, interestingly, the parallel postulate doesn't seem that exciting, but it caused a lot of controversy in math, because a lot of people that did math thought that we should be able to prove the parallel postulate. It shouldn't be a postulate, it should be a theorem. So a lot of mathematicians spent a lot of time trying to prove the parallel postulate, and it never worked out. What the mathematicians ended up doing was coming up with a bunch of postulates that were equivalent to the parallel postulate, rather than proving the parallel postulate as a theorem. And then what happened was, mathematicians said, well, what if we don't accept the parallel postulate? What if we say that there are more than one line through P that's parallel to L? Or what if we say that there are no lines through P that are parallel to L? And what happened when they did that was, turns out that they invented different kinds of geometry. So for example, on the surface of a sphere, there are no parallel lines, because all of our lines intersect at if we define, depending on how we define a line on a sphere, our lines go through the North Pole and the South Pole. So they all intersect at the North Pole or South Pole. So those lines are not parallel. In space, scientists believe the space is the shape of space is kind of hyperbolic, which is like the surface of a saddle on a horse. In space, there are an infinite number of parallel lines through a point because of the way the space is curved. And we'll talk about how that. I'll mention how that affects triangles in those different kinds of geometries also. So the parallel postulate led to a lot of things. A lot of mathematicians kind of arguing back and forth, but in the end, it led to the invention of new kinds of geometries. So parallel postulate, it doesn't seem like a big deal when you write it down, but it turns out it is a pretty big deal in math. And it also turns out, just a little kind of a side note, what we wrote down here is not the parallel postulate that Euclid used. This is called Playfair's postulate, named after one of the mathematicians who tried to prove the parallel postulate as a theorem, came up with this way of saying the parallel postulate. All right, now let's talk about triangle sum. Now that we have the parallel postulate, we have everything that we need. The triangle sum theorem. So here's what we're going to do. We're going to start with a triangle. Just any triangle, doesn't have to be any kind of special triangle. And I'm going to call it triangle ABC. And I'm going to label the angles 1, 2, and 3. All right, so we're going to be given triangle ABC. We have a triangle. We want to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180. All right, so we'll do a 2-column proof. Statements and reasons. I'm not going to rewrite our given that we're given a triangle, and it doesn't seem like we have much to go on. All we have is that we have a triangle. But here's how we're going to start. I'm going to construct a line through this vertex, through vertex C, that's parallel to the base of the triangle. So this kind of looks like our opener. And I'm going to call that line L. And for my statement, I'm going to say L is parallel to segment AB. Well, what tells us that we can make a line through that point C that's parallel to the base of the triangle? Well, I have a line and a point not on the line, and I've just made a parallel line through that point. What tells me that that parallel line exists? The parallel postulate. Parallel postulate says we can make a parallel line through that point. Well, now we have almost everything we need. I'm going to number these angles up here by the parallel line, 4 and 5. And I'm going to say the measure of angle 1 plus the measure of angle 5 plus the measure of angle 4 equals 180. So I'm saying if I'm adding all these three of these angles together and getting 180 degrees. Why do I know that? Now, what do those three angles make up? Not a pair. We don't have a name for a linear triple, but they all three make up a line, right? Together they make up a line. So I'm going to say they form a line. Angles form a line. We don't have a name for, we don't really call them linear triples, but that's kind of what they are. Not a bad name for them. All right. Well, now I'm going to say that the measure of angle 2 equals the measure of angle 4, and the measure of angle 3 equals the measure of angle 5. And why can I say that? Here's my parallel line. Those are alternate interior angles. Now we're set. Because this tells me that measure of angle 4 equals a measure of angle 2. And this tells me that the measure of angle 3 equals the measure of angle 5. So I'm going to plug those in to this equation where all those angles add up to 180 degrees. So I'm going to say the measure of angle 1 plus the measure of angle 3 plus the measure of angle 2 equals 180 degrees. Well, what tells me that I can take this and plug it in there, and take that and plug it in there? Substitution. And that's exactly what I was trying to show, that the angles inside the triangle added up to 180 degrees. So really we need two things. We needed to know that when we have parallel lines, alternate interior angles are congruent, and that we can construct that parallel line. And now we've shown, now we know why, all the angles in a triangle add up to 180 degrees. It's because of the parallel postulate. To me, it's a kind of exciting to know that this isn't some magical thing that someone pronounced sometime. Now we know enough geometry that we know this thing that we've accepted is true for as long as we've done math, almost. That's a pretty cool thing. Now, in other kinds of geometry, I mentioned that the arguing over the parallel postulate led to different kinds of geometry. In other kinds of geometry, we don't have the angles in a triangle adding up to 180 degrees. So on a sphere, the triangles end up kind of stretched out like this, and the angles in a triangle add up to more than 180 degrees. And on that saddle shape that I talked about, a triangle kind of looks squashed in like this, and the angles add up to less than 180 degrees. And what the exact number that they add up to depends on how curved the surfaces are. It's the fact that we're talking about a flat surface that our angles add up to 180 degrees. So angles in a triangle adding up to 180 degrees doesn't sound like it's really that special, but it really is kind of right at the doorway to all different new kinds of math. Non-Euclidean geometry is kind of interesting. All right, questions on our proof here? All right, there's one other thing that we need to talk about today. The exterior angle theorem. And the reason that we're talking about this now is that now that we technically know that all the angles in a triangle add up to 180 degrees, we can figure out other stuff. So let me draw a picture here so we know what we're talking about. So it's just a triangle, but I'm going to extend one side. And I'm going to label the angles like that. And what we're going to say is angle 4 is an exterior angle. That makes sense because it's on the outside of the triangle. It's on the exterior of the triangle. We're going to say angle 1 and angle 2 are its remote interior angles. Remote just means they're far away from it, and interior means they're inside the triangle. So those are the remote interior angles. Now I want to talk us through what we're going to say for this theorem because we know enough to figure it out now. What do all the angles inside the triangle have to add up to? 180. What do these two have to add up to? 180. So if angle 4 and angle 3 add up to 180, and angle 1 and 2 plus angle 3 add up to 180, how are 1 and 2 together related to angle 4? We take those two together and add them to 3 to get 180. We take angle 4 and add it to 3 and get 180. They have to be the same. That's exactly what we're going to say. We're going to say the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And in words, we'd say an exterior angle of a triangle is equal to the sum of the measures of the remote interior angles. And I should say the measure of here. An exterior angle is equal to the sum of the measures of the remote interior angles. And we figured that out. The way what we talked about, talked it through verbally, is exactly how we would prove it. We would say 3 and 4 add up to 180, 1, 2, and 3 have to add up to 180, and we would substitute measure of angle 1 and 2 for the measure of angle 4. So exactly what we just said in words, that would be our proof. Now the nice thing about, now that we have the triangle sum, we know about exterior angles. Often, just like with our angle puzzle the other day, there are more than one way that we can go about solving problems now. We can kind of pick the way that we like the best. So I just want to go through a couple of examples using the exterior angle theorem and triangle sum, and talk about the kind of different ways that we could work on these problems. These are the kinds of problems that you may see on the Chapter 3 test. So we have this big triangle split into two triangles. And we want to find x, y, and z. Now there are lots of ways that we could approach this. Is there an angle that jumps out at somebody that seems like it would be the easiest to find, easiest to start with? Yeah, Isabel. X seems like it would be pretty easy. Because if we look at this triangle, what do we know that all those angles in that red triangle have to add up to? 180. So to find x, we're going to add 32 and 46 and subtract from 180. So I could say x equals, the other way I could write that, 180 minus 32 minus 46. And I get that that is 102 degrees. So I agree that was one that jumped out at me that seemed like the easiest. What looks pretty easy to find? Yeah. Y. And how are we going to go about that? Right, these two are a linear pair. So we're going to subtract from 180. So y equals 180 minus 102. So we get 78 degrees. The other way that we could think about y. For this red triangle, y is an exterior angle, and 46 and 32 are the remote interior angles. So we could also say that y equals 46 degrees plus 32 degrees, which just ends up happening to be 78 degrees. So we could also think about it that way. Well, now we're set for angle Z, because angle Z now in this green triangle, we know two of the three angles in that triangle, and I could say Z, so we're going to add 36 and 78, subtract from 180. 180 minus 36 minus 78, and I get angle Z is 66 degrees. Anyone see a different way that we could have started with angle Z? What if we had looked at this big blue triangle? And this angle is 36 plus 32. That whole angle is 68 degrees. And we could have added that 68 degree angle and the 46 degree angle and subtracted from 180 to find that angle Z inside that big triangle. So we could have done it that way as well. So often with these kinds of problems there's more than one way to go about it. We can use triangle sum, we can use exterior angles, a lot of different ways. So then if we would have figured out angle Z, then we could have figured out angle Y. Angle X is the sum of the remote interior angles. So lots of ways to go about that one. All right, questions there? Okay, let's look at another example, this time with an exterior angle. So there's my triangle. I'm going to call that angle 1, 46 and 41 degrees. And we want to find the measure of angle 1. Again, a couple ways that we can do this. Anybody want to help us out with telling us one way that we could do it? Yeah? Yeah, this is an exterior angle. What measure? Angle 1 is an exterior angle. So the measure of angle 1 has to equal 46 degrees plus 41 degrees. So what do we get? 87? What's another way? Well, can't we figure out this angle? Because all three of the angles in the triangle have to add up to 180. So we could say, if I call this X x equals 180 minus 46 minus 41. And then these two are a linear pair. And I would get the same answer. So we could find the angle inside the triangle first, and then subtract that angle from 180 degrees to get that. So what would that come out to be? 93? Is that right? And then we could say the measure of angle 1 is 180 minus 93, which is 87. So we could do it that way also. If you don't remember about exterior angles and the remote interior angles, you can always use triangle sum. All right. One more example, just a slightly different, a similar problem, but slightly different setup. Here's my triangle for this one. We'll put the exterior angle down here. And I'm going to say this is 119 degrees. That's 2, and that's 46 degrees. And we want to find a measure of angle 2. Oops, sorry, not 46. That was the other example. 53. I grabbed that 46 from there. All right, couple different ways that we could approach this one. Anybody want to get us started? How you would go about it? Yeah? Okay, we can figure out this angle in the triangle. So we could call that x. So x equals 180 minus 119. Which is, what does that come out to? 61. And then we know that all three of the angles inside the triangle have to add up to 180. So we would say the measure of angle, let me write this angle in here, so that's 61 degrees. Measure of angle 2 has to be 180 minus 61 minus 53. And when we do that arithmetic, I believe we get 66 degrees. Is there another way we could have done this one? Or, well, I'll restate. There is another way we could do this one. Yeah. Right. You set it up basically exactly like we set up the last one. We know that 119, the other way we could do it, is 53 plus the measure of angle 2. When we add those two together, they have to equal the exterior angle. So we would do measure of angle 2 is 119 minus 53. And we'd get the same answer. So we can use the exterior angles and the remote interior angles, or we can use triangle sum. So it's nice, the more tools we have, the more options we have for solving problems. And a student in the last class said, do we ever have to use a specific method to solve a problem? And I said, and sometimes a book will ask you to use a specific method, but on a quiz or a test, it would be like this: find a measure of angle 2. So whatever method makes the most sense to you, as long as it's mathematically valid, it's not something you just made up, that doesn't necessarily work. It seems like a way to do the problem that maybe not be the right way. As long as you do the problem mathematically correctly, you're going to get your credit. All right. Now there will be some things in the future where I'll ask you to solve a problem using a particular method, but not in this bit. So page 175, 10 through 20 even, 21, and then 22 through 34 even. And we didn't have any homework last time?